Alright, so today we're going to talk about hardware backdooring. So just a bit of disclaimer, I'm not a terrorist. That being said, if you read the abstract, you already know that everything is open source. So like there is nothing much to release. The whole point of this talk is to demonstrate something you somehow probably know a little bit, which is that the x86 architecture is massively plagued by legacy. I still think the talk is relevant because we're trying to, you will see that the backdoor we're doing is orders of magnitude better than existing work. Alright. So we'll start by a bit of architecture, trying to introduce the problem and how we engineer this backdoor. We'll do a bit of an overview of the state of the art. Then I introduce you the proper backdoor itself. And we'll discuss a bit of cryptography and why it's actually not helping. And to finish, I'll explain you like how we can extend this work to backdoor like a proper nation state. Woohoo. Alright, so this is a sexy slide, or not so, or maybe not so much. I basically started working with computers by disassembling viruses and reading assembly when I was like 15. And nobody told me it was art, so like it didn't seem as such. I'm a big fan of like anything low level, to be honest. And I think hardware backdooring is like pretty much the limit where you can go. So what's relevant? We do, I'm part of the organization of a conference in Paris. It's called Aki to Agosum. Alright, so for the sexy slide, that's the Aki to Agosum t-shirt. If you're fond of cryptography, anything low level, feel free to submit. And if you don't understand what I'm saying, I'm French, I learned English in India, and I live in Australia. So that's 3 degrees in, as pure as it gets. So if at any point in time, like you really do not understand what I'm saying, please ask me to reformulate. Alright, let's start with a bit of FUD. So in case you've been hibernating for like the past few months, there was a report for the US Senate where they basically realized that every computer is built in China nowadays. I mean, even if it's designed in Western countries, it's essentially manufactured based on components coming from China anyway. So this leads to a bit of, how can we guarantee that this hardware is not backdoored? So a bit more FUD, like if you've read the media recently, like it's very much in the air to say that China is backdooring. I'd like to say, I'd like to go a bit more technical, like is it actually credible? Is it possible to backdoor hardware at all? For instance, in France last week, the government realized that all the routers we have on our core network is basically UI or ZTE. And they said, wow, that's scary, let's change everything and buy Alcatel Lucent instead. Alright, so enough FUD, let's talk a bit about architecture. So let me introduce you to the problem. This is the problem. So this is of course the x86 architecture. It was designed in 1981 and it has evolved very little. So basically you have to the bottom you have what we call the super I/O, to which the very slow peripheral are connected, like a floppy, the mouse, the keyboard. Then you have the source bridge, which is a bit faster. Typically your Ethernet card, your CD-ROM, your sound driver would be there. Then you have the north bridge, where much faster peripherals are connected. So typically following the PCI extension. So it could be like, gigabyte Ethernet, WiMAX, or video. So what's the big problem? There are actually two problems. The first problem is that at each layer, so say you take the soft bridge, you have a CD-ROM driver and you have an Ethernet card. So they are like very much physical peripherals. They both contain firmware, which allow to control their behavior. and allow software, I mean from user land and an operating system to actually interact with them. The big problem is that your CD-ROM driver can control your network card, and vice versa, actually. And this is a bit unexpected. Another problem that we'll discuss later is that the TPM chip is actually very low in the food chain. And it's a passive chip, unlike on game consoles, for instance, where if you remove the crypto chip or if the software is actually not calling it, the whole thing won't boot. On x86 architecture, the cryptographic chip, which can contain like cryptographic keys, it's much like an HSM really. So it actually also provides functions to do cryptography and not just the keys. If you don't want to use it, you don't have to. So like, right, let me not spoil it. I'll get back to this later. A bit of state of the art. So, I mean, getting execution as early as possible has been a goal since pretty much the first viruses. Brain was the first acknowledged IBM PC virus back in the 80s. The work which is really relevant to us would be like the 2009 research from Core Security. They actually did, in fact, a BIOS firmware, and they did it the hard way. Like they took a Howard Phoenix BIOS, they identified where is the checksum function, they introduced new code inside it, hostile code, and they compensated the checksum. So in terms of reverse engineering, if you want to go this way, it's going to be pretty tough to infect a new motherboard. You need to reverse engineer again, like the whole firmware. Other work relevant to us is mostly bootkitting, which is something entirely different. It has nothing to do with the BIOS. It's the fact of booting a computer from a CD-ROM or a floppy and patch the kernel on the fly. So basically they all work the same way. You hook in the interrupt vector table interruption 13, which is anything which is disk related. So like if you want to write to disk or write to disk or read from disk in memory, one sector at a time, you do it through interruption 13. The whole point of the bootloader, which is you know, the master board record of the first bootable hard drive, is actually to unpack a kernel in memory. And once this is done, you never use the interrupt vector table again. Awesome. There must be a party or something. All right. So the idea is that if you hook this interruption 13, while the operating system is trying to load, while the bootloader is trying to unpack a kernel in memory, you can actually hook any read or write. And you can patch the kernel on the fly. And you don't have to touch the file system at all. Okay, so now let me get to the meat. So pretty much like you, I guess, I'm not being paid to actually write malware. That being said, let's imagine for a minute that we want to do malware. If I have to do one, I'd better make one which is actually awesome, because I don't want to do that again. So I want it to be persistent, not just between boots, but like even if you remove you know, physical parts of your machine, or if you remove the hard drive entirely. Like if you replace the entire operating system, I still want to have persistence. The stuff should be stealth, so we'll see that it's actually possible to make a malware where 0% of hostile code is on the machine, not even on firmwares and PCI firmwares, etc. Ideally, it should be portable, as in OS independent. Of course, we want remote access, we want to be able to push remote updates, even if we're going to backdoor essentially PCI expansion ROMs and the BIOS firmware. Okay, when you come to state level quality, there are basically two features which make it like, right, this is usable by a state. The first one is plausible deniability. It's the fact of saying, well, you know, I mean, it's offering another alternative to explain why something went bad, in case you discovered. Saying, for instance, oh, you know, it was a mistake or something like that. And this second alternative allows you to, you know, in case people really insist, like, oh, you tried to do evil, you can say, no, you're a conspirationist. The other one is non-attribution, which is really saying, it wasn't me. Or usually nowadays it's like, it wasn't me, it was China. If we get make a backdoor, I want it to cross network perimeters, bypass firewalls, authentication proxies, etc. Because like they are so abundant in corporations nowadays. I want some degree of redundancy, and it's needless to say, I don't want it to be detected by any antivirus. All right, let me explain you how it works, roughly. Sorry, I'm a bit sick. All right, so this is a typical corporate network. So you have the users, you have some toys in the middle, can be like IDS, IPS, you know, gateway with firewalls, whatever, with antiviruses, whatever. And you have a firewall with proper DNS segmentation, which allows only HTTP after authentication. So basically, if you want to reach the network, it's going to be a bit tough. It's supposed to work this way. The user is supposed to authenticate against the firewall before reaching the internet. So this is all it's supposed to work. What we're really going to try to do is this. We're going to come with a Wi-Fi router, have the BIOS try to connect to this Wi-Fi router, and if we do that, like basically all the IPS, IDS, honeypots you may find in the middle are basically going to be useless. That being said, if it doesn't work for whatever reason, we can still default to using Ethernet. Okay, so let's go to the design. So instead of starting my malware from scratch, like most virus authors do, I took advantage of open source software. And I think it's actually a massively good idea for several reasons. So the base component is core boot, which is the back end of a BIOS. Basically, when you boot your computer, the first software which is actually executing in memory is responsible for discovering where is the RAM, where is the hard drive, where are the peripherals. So this is the role of core boot. CBIOS is the front end of the BIOS. In the core boot language, it's a payload, but I'll use another. I will define something else as a payload. So CBIOS is really responsible for creating an interrupt vector table in memory. And if you have core boot plus CBIOS, you can actually boot an operating system. An amazing thing about core boot is that it's super modular, and you can actually embed any PCI firmware to control like peripherals directly inside the main firmware. So I'm using one which is called IPXE, which is an extension of the PXE standard, which instead of doing just DHCP and FTP, can actually boot an operating system remotely over, say, HTTP, and instead of using just DHCP over Ethernet, IPXE allows you to use Wi-Fi, WiMAX. It knows a bunch of protocols, like it has a full TCP stack, and even higher protocols, like it has FTP, HTTP, even HTTPS. So that's making it pretty awesome. Like you don't have to do all that yourself again. And then we use a bunch of payloads, which are basically bootkits. I'll get back to this. So I was mentioning non-attribution. One of the benefits of using open source is that it wasn't written by me. It's actually written by something else, but really. In terms of development, I mean, if you ask journalists, like, yeah, Stuxnet took years to develop by a whole team of specialists. All right, so I did this by myself in 4 weeks. And I think it's really hard to detect as malicious, because all those components are actually not malicious, apart from the payload. But Well, there is a trick. So it works like this. We're going to flash the BIOS. Let's assume we are a manufacturer in China or whatever, or I'm just part of the supply chain delivering your laptop. Like when you buy your laptop, anybody who touches it before you can actually backdoor it. So we're going to flash not only the main BIOS, but also a few PCI expansion ROMs. Like I explained to you, if we flash only the CD-ROM drive, we can actually control the network card. The idea is to, in case the BIOS is ever flashed by someone for normal maintenance, we can flash it back using using a PCI expansion ROM. We're going to boot a payload over the network, typically over HTTPS. And like I explained before, we're going to try to use Wi-Fi or WiMAX if it's available, which leaves no trace on the corporate network. So it pretty much looks like this. The core in blue is made of core boot, then CBIOS, which is the front end, and IPXE, which is really a PCI expansion ROM, but also embedded in the main firmware. In the main firmware, we're going to put in the BIOS. And then the only piece which is really malicious is the bootkit. But the bootkit never touches the disk, and it's not embedded in your hardware, in your PCI expansion ROM or in your BIOS ROM either. Instead, so execution goes like this. So your CPU starts in 8086 compatibility mode, in real mode, which is essentially a legacy thing. For you, if you have done like programming under MS-DOS, you know how painful it is to work with this. You don't have multitasking. You have only access to the first megabyte of memory also. So core boot gives execution to CBIOS, which is going to set the interrupt vector table, who itself is going to call IPXE to perform network booting. And the only malicious piece is going to be fetched every time you boot over Wi-Fi or Ethernet, if nothing else is available, over HTTPS. So there again, in terms of analyzing network traffic, deep packet analysis, this is just not going to work. We can use actually client-side certificates to ensure that there is no man in the middle during the HTTPS connection. Any questions so far? Okay, so in terms of the features we're going to embed in Rakshasa, we're going to try to remove the NX bit. If you manage to do this, every mapping becomes executable again. We're going to try to make every mapping in ring 0 writable. We're going to try to remove CPU updates. So I don't know if you're really familiar with this. Every CPU vendor has basically a way to correct mistakes, because like hardware has bugs also. If you look at the errata in the Intel CPU, it actually has a bunch of small mistakes which allow to modify the control flow of execution. So it's actually big mistakes. When this happens, instead of replacing every physical CPU, what they do is pushing a small microcode, which is digitally signed by the manufacturer, typically Intel or AMD, inside the CPU and compensate for this problem. This is typically performed at BIOS level. We're going to remove anti-SMM protection. SMM, which stands for System Management Mode. It's like ring -0 or patch mode, really. If you're familiar with this, the problem introduced by Duflo regarding SMM at ConseQuest in 2006 and 2009, there is basically a generic exploit locally which will allow you to get to ring -2, so even the operating system will not know what you're doing, and you're switching essentially to a 16-bit mode which has higher privileges than the kernel, so like you can patch back the kernel if you will. We're going to try to disable randomization, and eventually we're going to load a bootkit. So the bootkit was actually contributed by Piotr Bania. If you're familiar with Conboot, it's a modified version of Conboot to like remove the fancy displays and stuff, but essentially it's Conboot. All right, let's do it. So if we want to remove the NX bit, first off, the NX bit is a model-specific register. So if you read the AMD 64 manual, I mean, AMD was the first one to actually introduce an NX bit in '97. So it's pretty smart to look at how they did it before it was actually copied by Intel. So there is a specific bit in a model-specific register, which is called the extended feature enable register. You hardly ever use that, honestly. If you flip the bit 11, every mapping becomes executable again. So like, to do this, you first must make sure that your CPU actually does support NX. And essentially what you do is like the 3 last lines, you read the content of this model-specific register, you flip bit 11, and you write it back. The only difference is that we don't do MOV with model-specific registers. We use those RGMSR and WRMSR instructions to read and write to model-specific registers. So this is only going to work if your CPU supports it. Okay, changing every mapping, this is a difficult part, right? After we have the demos and the fancy shit. So basically in CR0, control register 0, bit 16 defines if what is mapped in memory is writable or not. So it's actually something pretty common in viruses and in exploitation. If you've seen last year at DEF CON, Dan Rosenberg talking about remote kernel exploitation, he explained how to do it. So you read control register 0 into AEX, you flip the bit in question, you write it back, and that's it. You just, every mapping just became writable in ring 0. So it doesn't work for userland, just for ring 0. But like, if ever you have a vulnerability affecting the kernel, you're going to be bang vulnerable. It's going to be a lot easier to exploit. Removing CPU updates, that's pretty easy. You just remove the microcodes from core boot, and like there is nothing else to do. Regarding SMM, so typically the protection against SMM is to set a bit, which is called dlock, which prevents you to talk ever again to, to switch ever again to system management mode when you trigger an SME. So since core boot actually does not support this feature, we have nothing to do, and the shellcode to do it is just a knob. Disable ASLR, all right, that's tougher. It's very much OS dependent because I mean, hardware is not responsible for randomization, it's very much a software thing. The idea is that if you want full ASLR, it has to be done in kernel land. If you don't have full randomization, it can actually be done in userland by patching the dynamic linker like Stefan Hesser did on iPhone, for instance. But if you want full ASLR, like the base address of your main binary has to be randomized, and only the kernel can do this. So the idea is actually to patch the seed, which is going to be used to create this randomization. And if you patch this seed, so it's been identified, for instance, for Windows 7 by Kumar and Kumar at Hack in the Box in 2010. If you patch this seed with a known value, your mapping is going to be repeatable all the time. So what happened is that there is no randomization anymore. So if we manage to get all of this down, we have permanent lowering of the security of any operating system, because we actually even lowering the security of the hardware. Like if we remove the CPU updates, what we're really lowering is the security of the hardware. And since NX was basically introduced in '97, you're back to the security of 97, which with the knowledge we have of exploitation today, is Christmas time. Indeed, since we do this in the firmware embedded in your hardware, even if you change, say, your hard drive entirely, or you replace the operating system, we still have persistence. Just a little bit more of theory, and then we go, I promise, to the demos. So currently, the bootkit I'm using is ContBoot, a slightly modified version. So it's capable of booting any version of Windows, 32 or 64-bit. That being said, if you want to be able to, I mean, when Windows 8, for instance, is gonna be released, we want to be capable of owning this. So instead of embedding ContBoot directly into core boot, into the BIOS firmware, which we could do, it's a much better idea to do it remotely and to fetch it every time at boot time. Sorry about this. So we write nothing to the hard drive, so there is zero evidence on the file system. Like I told you, we try to have as little evidence on the network also as possible. The code which is flashed on the motherboard or on the PCI devices is not hostile, so there is zero reason for an antivirus to spot it as hostile, and if they do, it's actually a false positive. Alright, I'll get back to the rest later. So I think it's actually a good approach to start using open source to make viruses. In terms of portability, core boot is capable of, I mean, it's supporting, let me show you. So we said the state of the art, the work for, from core security is to support one BIOS, which is like several motherboards. Core boot is actually supporting that many. So I had nothing to do, like. Alright, so this is pretty epic. The amount of reverse engineering they had to do is actually massive. Like, for most of them, they don't even have the data sheets. What they do is they use a physical device which just gives you the last error code. So imagine trying to port a BIOS with that much information. It's sick. Anyway, and the good thing is that I don't have to maintain my backdoor, they do it for me. In terms of modularity, like we said, we can embed everything inside the BIOS itself or put several components on the PCI firmware on the BIOS itself, and this gives us a degree of repeatability, if you will. And in terms of network stack, I don't know if you've ever done any kind of programming in real mode, but having trying to do a TCP connection is virtually impossible because you don't have multitasking. So what they do is actually cheating. They switch to protected mode to be able to have multitasking, etc. And then they go back to real mode before transferring execution to the master boot record. From the master boot record perspective, it's invisible. Alright, let me tell you a bit of the configuration files of IPXE. I think I'm going super fast. Alright, so we can try to get DHCP, and if it fails, we can default to a static IP. We can do awesome stuff with web application, like we can authenticate against a web application, we can send parameters. It has actually a few macros like or to send your IP address and your MAC to a web page on the internet. So from there we can send emails, we can do router farming. The image emulation is the limit really. We can even change the bootloader, change the configuration file of IPXE from another server on the internet, which avoids us to hardcode anything. Then when you're happy with all that stuff, you say actually, oh, I changed my mind, and let me actually boot the proper bootkit, which is really made of two parts, memdisk, which is going to be the kernel. So you can fetch it, for instance, over FTP from a Chinese website, if you will, or just over HTTP. And same thing for the main bootkit. I hid them into PDF files, but it's really very much like the kernel renamed as memdisk.pdf, so that if for some reason there is some kind of network analysis, it's going to be harder to check. All right, let's go to the, thank you for your patience. Let's go to the demo. This one is called Evil Remote Kernel on Edge of Death. Okay, I could actually flash it on my main box, but like you would see nothing, which is not very visual for a demo. So instead, I'm going to use KVM, which is an emulator, which is also supported by Coreboot. I'm just going to start a small network sniffer for you to see what's happening. We're going to focus only on HTTP. Okay, so the whole command is this. So we start KVM, we specify a different BIOS from the one of KVM, which is actually my malware, Rakshasa. We tell him to be full screen. We want network connection. I actually have Ethernet here today. And you boot me a drive which is very much a Windows 7. It better work. It's not working. It is, all right. Okay, I will need someone innocent to type my admin password. Do you know my admin password? Oh, don't be shy. Can you come over? Yeah, you mate. Yeah. So the idea that you know to use Windows? You choose any password you want. All right, and it's actually booted, right? So now, thank you, mate. So like, let's look at what really happened here. So first off, the application, the BIOS downloaded a second configuration file from a remote website, okay, using HTTP. This is very much an IPXE configuration file which tells him, all right, you're going to try to send me an email using a web application from the BIOS, and we're going to fail over. Just a, sorry, is it too small? Is it better? I don't know how to make it bigger on that stuff. All right, so the idea is that it's downloading an alternate configuration file, and then it's gonna boot on a, no, sorry, this is already the alternate configuration file. It's gonna boot on a blog, essentially, which is the blog I used last year for my Black Hat talk, because I'm too lazy. All right. We can see that actually these two files have very much been fetched. So this is a memdisk thing. And the other one is the actual payload, which is a recrafted Coreboot version. All right, so let me check my mails, because you guys are a bit boring. You could have applause there. So I'm a bit pissed. Okay. So if I go to my mails, I have a message from Rakshasa. You can read this. Sending me the IP parameter, like the IP, the MAC, the network masks, the gateway, and the DNS. Thank you. So this was actually a Windows 7 64-bit. How do you get to see this? Yep. But this is very much con boot, like it's going to work with any Windows really. Any questions so far? Okay, so let's go to more interesting stuff. Obviously, if we read the Apache logs, we have the traces also of, you know, what the IP address, the next mask, etc. So like we mentioned, we actually receive emails seemingly from the BIOS. This is before booting the operating system. I'd like to tell you about how to properly build a botnet. A botnet you cannot shut down. You must know that Microsoft is using signed updates. Why not do this for my botnet? If I want to make a botnet from a BIOS, I can very much sign the updates also. So that if law enforcement ever sees the CNC, the command and control, they will not be able to shut it down. Right? Because like this is how they do it, right? They hijack one server, one CNC, and they send a shutdown command. If you do that, there is still a problem, like the availability of a CNC. And to do this, what we can do is rotate the CNC every 5 minutes over the entire internet. And it's unlikely that you're going to shut down the entire internet to shut down my botnet. So one day it's going to be Amazon, one day it's going to be Google, one day it's going to be AT&T, oh, next day it's me. So I push my updates. And I think that if malware was actually doing this, which is not really happening today, it would just be impossible to shut down. Any question? Okay, let's talk about mitigation and in particular cryptography, because it's usually the one which comes to mind. So first off, we can very much do an evil-made kind of attack, booting a fake prompt, and TPM is not going to help you there. Because TPM is not enforced by the hardware. Even if you sealed your computer, you have full disk encryption, and you're using TPM, if I flash your hardware with Rakshasa, and next time I boot, I bring a fake logging prompt, you cannot see the difference. And TPM is not capable of enforcing the real full disk encryption login to boot. So this is a bit of a problem. We can do all the stuff like trying to brute force, etc. I showed that like at DEF CON 2008 if you're interested. So this is very much of a problem. The other problem is that even if full disk encryption is actually used, when you buy your computer, the hard drive is not encrypted. It's not possible. Well, if it was, like it would be encrypted with a password you don't know. So you would have to, or which is known by third parties. So to change the password, you would have to unseal the TPM, and bam, if you do that, you're vulnerable again. So anybody in the supply chain can very much backdoor your stuff because your hard drive is not encrypted, and therefore the TPM is actually not sealed when your computer is delivered to you. You may be asking about antiviruses. If you ask me, putting an antivirus on a server is pretty much as putting lipstick on your server. Let me show you why. We said the only component which is actually malicious is con boot. So I took the legit con boot version, which is like at least 3 years, maybe 5 years old, and is detected by 2 antiviruses on VirusTotal. Not bad. Then I encrypted it with a super elite packer called LZMA, which is actually the most common packer, most probably. It's the one used by Linux by default nowadays, and it's the one used by every BIOS I know. And the detection rate drops to 0. All right, I won't talk about this. You could be vulnerable if you actually change your network card. If your network card, you buy it on eBay, and it comes with a rogue PCI driver. At boot time, every PCI driver has the same privilege as the BIOS. So when your device is initialized, it could actually very well do the same thing, even if your BIOS is sane, and reflash the BIOS back from the internet. We're going to see that later. It's actually also possible to backdoor ESXi, or at least several versions of VMware, using raw PCI devices. So in terms of remediation, I suggest instead of trusting firmware you don't know, when you receive a computer, you flash it with firmware you can control. Typically, core boot is a good idea. If you're victim of an intrusion, because it's also possible to flash the BIOS if you get a remote root shell, you should not trust your BIOS anymore. But if you want to flash if you want something sound, since you cannot trust your kernel anymore, you should flash every PCI firmware and the BIOS at the same time using a physical device like this. And nobody has the time to do it. So I suggest you just throw your server away. I told you about flashing remotely. We just saw that we can boot a remote operating system. So since the flasher for most BIOSes is just a Linux and it's generic, flashing the BIOS itself remotely is a given. What's not a given is flashing other PCI expansion ROMs somewhere on your machine because they are very much hardware dependent. So say I want to flash the network PCI firmware. How do I do this? Well, we saw that IPXE can actually send the MAC address to the server. So the server can know the MAC address, from there it can deduct the Win number, and from the Win number it knows the manufacturer. And it can send back the appropriate tool and the exact version of the flasher which is appropriate for your network card. This is actually not a trick, it's something supported by IPXE, which is even better. Alright, so backdooring like a state. Everybody knows that only China does it. So we mentioned non-attribution and possible deniability. Non-attribution is a given because I mean, it's essentially free software. So you did not write it. You don't have to explain why you did not. You did not. For plausible deniability, I suggest instead of flashing, owning this, of putting a backdoor straight away, to use a remote vulnerability on the firmware, and such stuff does exist. The same guy who found the SMM thing actually found a remote vulnerability on the firmware of Broadcom network cards. It's just not enabled by default because there is a slight setting to do, but like if you change this setting, this is slightly better. I mean, you can claim it's a mistake and an honest mistake. It's not a backdoor by itself, right? But it allows you to own the computer remotely, get a remote root shell, and from there you can bootstrap the thing, like flash the BIOS from other PCI devices, etc. Do your evil filtrate data, etc. And when you're done, you restore the BIOS, every PCI firmware, and you're done. Zero trace left. So more demos. If you read this book, Millennium, it started to be bullshit around page 50 when she boots a remote operating system from the guy she's infected. Turns out this is actually possible if you have a link which is fast enough, typically gigabit Ethernet and a SAN. So this is again supported by IPXE. Let me boot a demo quickly. Okay, so I don't have a SAN, so we'll just do it booting a CD-ROM, but it's essentially the same thing. Sorry, let me CD-ROM. Oh, I think this is totally legit. All right, Windows is booting. I'm going to do the rest while it's booting. There is also a small problem of BIOS graphics. Like when I booted it, you didn't see any graphics, but like it's a fake problem because like other versions are better than CBIOS actually have better menus, and you can embed a proper graphic, a boot splash when booting. So for instance, you can have stuff like this. You can have a wall invaders. I'll show you in the question room if you want. When it comes to UEFI, which is often mentioned as something better than the BIOS, Core boot is actually 100% compliant if you change cBIOS by Tiano Core, which is another open source project. The only difference is going to be that the bootkit you're using, Comboot, is not going to work. But if you saw the work of Snare this week at Black Hat, he actually wrote such a bootkit. So like, I don't see why people actually trust this technology either. Best thing, this is not a vulnerability, so there will be no patch for it. It's just bad design. I mean, we cannot really blame IBM for making the mistake in 81, but we keep on having like retro compatibility and stuff. Just to remind you, Microsoft in 95 did not anticipate the internet. When you bought Windows 95, the shares were open because it was supposed to be used in LANs and stuff like that. So like imagine the kind of anticipation IBM could have won in 81 when creating every PC. And since I got the question, yes, a Mac is a PC nowadays. Any question? We're going to see just, yeah, I think that's very legit. All right, we're going to move to the other room for the questions. Thank you so much for your attention. All right, so today we're going to talk about hardware backdooring. So just a bit of disclaimer, I'm not a terrorist. That being said, if you read the abstract, you already know that everything is open source. So like there is nothing much to release. The whole point of this talk is to demonstrate something you somehow probably know a little bit, which is that the x86 architecture is massively plagued by legacy. I still think the talk is relevant because we're trying to, I mean, you will see that the backdoor we're doing is orders of magnitude better than existing work. All right. So we'll start by a bit of architecture, trying to introduce the problem and how we engineer this backdoor. We'll do a bit of an overview of the state of the art. I introduce you the proper cryptography, anything low level, feel free to submit. And if you don't understand what I'm saying, I'm French, I learned English in India, and I live in Australia. So that's 3 degrees in, as pure as it gets. So if at any point in time, like you really do not understand what I'm saying, please ask me to reformulate. All right, let's start with a bit of FUD. So in case you've been hibernating for like the past few months, there was a report for the US Senate where they basically realized that every computer is built in China nowadays. I mean, even if it's designed in Western countries, it's essentially manufactured based on components coming from China anyway. So this leads to a bit of, I mean, how can we guarantee that this hardware is not backdoored? So a bit more FUD, like if you've read the media recently, like it's very much in the air to say that China is backdooring. I'd like to say, I mean, I'd like to go a bit more technical, like is it actually credible? Is it possible to backdoor hardware at all? For instance, in France last week, the government realized that all the routers we have on our core network is basically UI or ZTE. And they said, wow, that's scary, let's change everything and buy Alcatel-Lucent instead. All right, so enough FUD, let's talk a bit about architecture. So let me introduce you to the problem. This is the problem. So this is of course the x86 architecture. It was designed in 1981 and it has evolved very little. So basically you have, to the bottom, you have what we call the super I/O, to which the very slow peripheral backdoor itself. And we'll discuss a bit of cryptography, and why it's actually not helping. And to finish, I'll explain you like how we can extend this work to backdoor like a proper nation state. Woohoo. All right, so this is a sexy slide, or not so, or maybe not so much. I basically started working with computers by disassembling viruses and reading assembly when I was like 15. And nobody told me it was art, so like it didn't seem as such. I'm a big fan of like anything low level, to be honest. And I think hardware backdooring is like pretty much the limit where you can go. So what's relevant? We do, I'm part of the organization of a conference in Paris. It's called Aki to Agosum. All right, so for the sexy slide, that's the Aki to Agosum t-shirt. If you found of peripheral connected, like a floppy, the mouse, the keyboard, then you have the source bridge, which is a bit faster. Typically your Ethernet card, your CD-ROM, your sound driver would be there. Then you have the north bridge, where much faster peripherals are connected. So typically following the PCI extension. So it could be like, gigabyte Ethernet, WiMAX, or video. So what's the big problem? There are actually two problems. The first problem is that at each layer, so say you take the soft bridge, you have a CD-ROM driver and you have an Ethernet card. So they are like very much physical peripherals. They both contain firmware, which allow to control their behavior and allow software,